stability is judged by ascertaining to what extent they can bear load or what is their elastic limit, etc. Hence, a knowledge of elastic properties of different materials is essential for different kinds of work, especially in engineering science and technology. Thus, the topic under the discussion is elasticity. Let's get the definition of elasticity. When a body is acted on by a system of balanced forces, the body may undergo a change either in shape or in size or in both, but it returns to its original shape or size when the system of forces is withdrawn. This property of substance is known as elasticity. The system of forces is sometimes called deforming forces. Let's now get familiar with some important definitions in connection with elasticity. Strain. Whenever a system of forces in equilibrium act on a body, the forces do not produce any bodily motion, but produce a relative displacement of the various particles of the body, causing a change of shape or size or both. This change is generally called the deformation or strain of the body. How can we measure strain? Well, it is measured by the ratio of the change in the configuration to the original configuration. Stress. When a relative displacement of various parts of a body takes place on the application of a system of deforming forces, a resisting force is called into play inside the body, tending to bring it back to its unstrained condition. This restoring force is called stress. Stress is measured by the force applied externally per unit area of the body. Let's consider the applied force to be inclined to the surface of the body. The component of the force normal to the surface per unit area is called normal stress. On the other hand, the component along the surface per unit area is known as the tangential or shearing stress. Perfectly elastic. If a body after being strained regains fully its original shape or size when the external forces are withdrawn, it is called a perfectly elastic body. Perfectly rigid. A body will be called perfectly rigid if it does not suffer any strain under any amount of stress. No substance is perfectly rigid, though glass is a very close approach to it. Perfectly inelastic. A body is said to be perfectly inelastic or plastic if it retains its changed configuration even after the removal of the external force, however large it may be. Partly elastic. In the practical world, we neither find perfectly inelastic or perfectly elastic bodies, but partly elastic bodies are readily found. A body is said to be partly elastic when, after the removal of the external forces, the body regains only a part of its original configuration. To study the elastic behavior of a solid material, generally a wire of the material is taken and gradually increasing loads are put one end of the wire, the other end being rigidly fixed to a stout support. Due to the loads, extensions in the length of the wire will take place and a graph drawn between the load and extension so produced provides us an easy means of studying the elastic properties of the material. The figure in the screen shows such a load extension graph for a solid material. It is seen that the portion of the curve from point O to point A is straight. It means that the extension is proportional to the load. If at any point between point O and point A the load is removed, the wire returns to its original state. So, the substance behaves as a perfectly elastic substance up to point A. The substance obeys Hooke's law up to point A. OA, the wire is said to undergo elastic deformation. Loading a little beyond A, the stress is not proportional to strain. The wire still remains elastic. This means if the load is removed, the wire gets back to its original length along the curve BAO. This behavior is shown up to a point B on the curve. This point is called the elastic limit or yield point. If the stretching load is increased beyond the elastic limit, the strain increases more rapidly. If the load is removed, say at point C, a permanent set occurs. The wire returns to point E instead of point O. OE measures the permanent extension. Under these circumstances, the material becomes plastic. If the deformation is increased further, the wire breaks at a point known as fracture point. In the figure, point D represents the fracture point. The stress corresponding to the fracture point is called breaking stress. Brass, bronze, and many other alloys, however, seem to have no fracture point. These materials increase in length beyond the elastic limit as the load is increased without the appearance of the plastic stage. Substances that elongate considerably and undergo plastic deformation until they break are called ductile substances. Metals like lead, copper, wrought iron are ductile. Other substances, however, break just after the elastic limit is reached. They are known as brittle. Glass, high carbon steels are brittle. A solid body is subjected to compression, then also the body acquires permanent set beyond a certain stage. This is known as elastic limit for compression. Within this limit, the solid body behaves just like an elastic body, and beyond this limit, it exhibits its plastic properties. The yield point in the case of compression is called the crushing point, which occurs if the compression is increased beyond the elastic limit. Beyond the crushing point, metals are said to be malleable. Then they can be hammered into flat sheets. Gold is said to be one of the most malleable metals ever found. A rapid change of stress on an elastic material produces elastic fatigue in it, which causes a degradation of its elastic property. The material may then break or snap at a stress less than the normal breaking stress, or even at a load within the elastic limit. Hooke's law states that within elastic limit, the stress applied is directly proportional to the strain produced. This law was established by Robert Hooke in 1678. According to this law, within elastic limit, the ratio of stress to strain is a constant. This constant is known as the modulus of elasticity. The following array of slides features step-by-step explanations for different kinds of strain, the corresponding moduli of elasticity, and the relationships among them. To shorten the video, the slides have been made to pass fast. So pause each slide to read the content between the lines.